Welcome back, Organic Chemistry 1, Chemistry 230, Chapter 7. We finally arrived to our very first chemical reaction that we're going to be studying in organic chemistry. Chapter 7 is titled Alkyl Halides, Nucleophilic Substitution and Elimination Reactions. For pedagogical purposes, I have decided to divide this particular chapter into two sections. Okay, so what is that? Those two sections? I will call it 7A and 7B. What's the difference between 7A and 7B? 7A will only cover about nucleophilic substitution. That would be 7A. Whereas 7B is going to be elimination reactions. Okay, so that would be 7B. Normally for my lectures, I only include 7A for exam 2, and 7B will be for the exam 3. Okay, so that's why I divided it. I'm also going to make two videos, one for 7A, nucleophilic substitution, and another video, 7B, for elimination reactions. Those two reactions are extremely connected. They are really, they use basically the same starting material, but they have different outcomes. But the foundations, they share many things in common. But since here in nucleophilic substitution, we will study two reactions. And here in elimination, we'll also study two reactions. Those reactions compete to each other. Since they use the same starting material, of course, it makes sense that they will compete. So sometimes they will do nucleophilic substitution, sometimes they will do elimination. How do I know? How I avoid to get confused? That's why I split this chapter into 7A and 7B. So in my questions, either the quiz or the exam or the final exam, it will be clearly stated. Please determine the substitution product or determine the elimination product. It will be very clearly stated because these reactions, there is a competition between these two, as we will see later, right? So chapter 7A, nucleophilic substitution, and 7B is going to be elimination reaction. But for now, we will only do substitution reaction. Here in this very first slide, we have an overview of the reaction we will study. Remember here, our goal is going to do substitution today. And as the name says, substitution, it is really you are substituting. In this case, group X is substituted by the group NUC, right? So which is the nucleophile. So that X group, which is we are going to be start calling it a leaving group, is substituted by another species, which is called a nucleophile. That nucleophile, even though here is shown charge, but sometimes the nucleophiles can be neutral or charge. Okay, so the definition of a nucleophile, we already study it, right, on chapter 6. Nucleophile is a species which can be an ion, a neutral compound that has lone pair of electrons. One lone pair is enough. 1, 2, 3 lone pairs of electrons, and is able to donate them. It's very important that last statement, that is able to donate them. Electrons that are involved in resonance greatly decrease their nucleophilicity. So for example, if you tell me like which one is more nucleophilic, this alcohol or this alcohol, I will definitely tell you that this alcohol is more nucleophilic. Why? Because those electrons in this second compound, they are involved in resonance. There is resonance going on here. So participating in resonance makes electrons less available because they are moving back and forth. So resonance is actually a bad thing for nucleophiles. You don't want to have your electrons in resonance if you want to do a nucleophilic attack. Okay, so going back to substitution, we have what we call here, let's get used to this terminology. We will have here a substrate. Okay, so let's write it here, substrate. I will use that term very often, substrate. The nucleophile, okay, we know that, and that one will be the product. And we have a side product, but I mean, my most important product is this particular compound. In elimination, which is the second reaction, the purpose of how to differentiate a substitution from elimination reaction is that elimination will always produce an alkene. A double bond will be produced, always, okay? So as I said, we have two reactions here and two reactions here, right? They share many features in common. So elimination reaction will actually be easier for you guys. Why? Because it's the same terminology, the same foundation, the same exceptions, the same steps that you will see for elimination and substitution. So let's get ready with this substitution reaction. And once you guys dominate the substitution reaction, you'll definitely have an easy way easier way in elimination reactions. Okay, so our substrates are we name here, right? So they are normally going to be alkyl halides. I know that we haven't talked about alkyl halides that much, but alkyl halides are compounds, right? So that let me open my camera. Yep. So there is alkyl halides are compounds that have should focus automatically. Alkyl halides are compounds that have chlorine. Like chlorine, can be bromine, can be iodine. You say like, oh, what about fluorine? Yes, fluorine too. But as we will see soon, fluorine is a bad leaving group. So it is, even though it's an alkyl halide, but really we're using the alkyl halides as good leaving groups. So we want those groups to eventually leave the molecule, right? So we don't want them inside. So out of those 4 halogens, good leaving groups are chlorine, bromine, and iodine. Fluorine is also an alkyl halide, I know, but it's really not the best leaving group that we can have in chemistry. Okay, so when we're talking, and then by alkyl halides, remember that I mean alkyl groups. Alkyl group means that this carbon must be sp3. Okay, so for example, this compound is an alkyl halide. This compound is an alkyl halide. This compound is an alkyl halide. Okay, so what is not an alkyl halide? This is not an alkyl halide. This is an alkenyl halide. Alkenyl. Why alkenyl? Because alkenyl comes from alkene, double bond. It's not. So this carbon is sp2. If it's sp2, you cannot do substitution and you cannot do elimination. Same thing happens with aromatic or with benzene rings that have bromine there. Bromine or any halogen. I mean, I'm just using bromine as an example. But really, if you look at this carbon, right? This carbon is sp2. Therefore, I can't do any substitution. I can't do any elimination. Why? Because you only do these reactions on atoms or leaving groups that are occupying an sp3 carbon. Has to be sp3, right? So you happen to see, let's say, that chemical reaction, a question that they ask you, oh, what about this compound? Which one gets reacted? Of course, this one will be the one. Why not this one? What? Because this iodine is sitting on a carbon that is sp2. This bromine is sitting on a carbon that is sp3. So out of the two, only this one will react in the substitution and elimination reactions, right? So this is going to be clear with the alkyl halides. Alkyl halides are not the only leaving groups, but we will use it as the most important leaving groups. Okay, I'm just writing what the name. Leaving groups, chlorine, bromide, and iodide. Now, the big question is like, okay, professor, so these are the 3 leaving groups, but is there any preference? Which one is a better leaving group? Is there any category, any ranking? So even though they are all halogens, but is there any trend? Yes, iodine is a better leaving group than bromine, and bromine is a better leaving group than chlorine. That's why fluorine is really a bad leaving group. Why? Because the property or capacity of being a leaving group really increases this direction. So that means this is an excellent, this is very good, this is good, and this is bad. Okay, so that would be more or less the trend. And this one is really the trend of the periodic table, right? So it follows. This should be a reason. The reason is the size of fluoride. Fluoride ion is too small, so it is unstable if it is a leaving group. I mean, it exists as an ion, right? So alkyl halides can undergo elimination reactions, right? When treated with a base. That's the difference between a substitution and elimination. If you notice, I didn't really go over the equation for elimination, but here in substitution, we use a nucleophile. Whereas here for elimination, we use a base. What's the difference? We will see the difference more in detail when we study elimination. So for now, let's just assume, since we're only studying substitution, let's just focus on nucleophile. Nucleophile is a species, neutral or anionic, right, with a negative charge, that has lone pairs of electrons available and is able to donate them, right? So let's leave it like that for now, and that would be really our starting point to determine the how a substitution reaction works. Right. So what do nucleophiles and bases have in common? Yeah, I mean, as I said, like they really, the difference, I mean, I can use this slide, I mean, to tell you the difference right now. Between a nucleophile and a base is really the ability of attacking a particular target. Okay, so I'll just use that, right? So nucleophiles versus bases. Okay, what's the difference between a nucleophile and a base? Nucleophile, as you notice, they both have the same definition. They are species, neutral or charged, that they have lone pairs of electrons and they are able to donate them. They both have the same definition. What is the difference between a nucleophile and a base? The difference is that a nucleophile will always target carbon. Okay, whereas a base, as we know, bases react with acids. Acids are rich in hydrogens. Therefore, if you see something, for example, OH minus, okay? If I see that the OH minus is attacking a carbon, I will say, okay, the OH is behaving as a nucleophile. Why? Because it's a species that is negatively charged, has lone pairs of electrons, and is able to donate them to who? To carbon. Then it's acting as a nucleophile. What if this same OH, instead of attacking a carbon, now attacks HCl? What about this? Now, in this case, OH also is a charged species, is negatively charged, has electrons, and is able to donate them, but it's donated into a hydrogen. Now, in this case, it's behaving as a base. In this case, with carbon, it was behaving as a nucleophile. Okay, so hopefully it is clear, right? The difference between a base and a nucleophile. So really, the definition is the same. They are electron rich, that they're able to donate those electrons. The difference really comes from who they are attacking, right? So in this case, attacking a carbon, nucleophile, attacking a hydrogen makes them a base. Okay, so hopefully that difference, because I know that this should be very curious about what is the main difference between the two terms, right? So let's continue now. All right, so in our here we have again the elimination and the substitution products, right? So remember, we are only going to be dealing with the substitution. Substitution and elimination, as you can see here, they occur simultaneously, right? So for example, the same substrate, I have a chloride here with NaOH, you get an elimination and substitution product. The major product is elimination. But as I mentioned in the beginning, in the very first slide, we are not really going to analyze an equation in which you have to determine or analyze which of the two is the most predominant, which of the two is the major product. I will divide it very clearly. Give me the substitution product or give me the elimination product. I will never ask you, give me the product. No, because if I ask you to give me the product, then you will have to state which one is the major, which one is the minor. And that is a more challenging task, okay? So only with a lot of practice and a lot of real experience, even me as an undergraduate, I wasn't really clear which one is an elimination product, which one is a substitution product, right? Major, minor. No. So that's why for you guys, I'm going to make it a little bit easier. And then I will tell you, for example, right now, 7A, we're only studying substitution reactions. Therefore, I'm only expecting you to give me the substitution products. On 7B, chapter 7B, I will ask you elimination products. Do I have to consider substitution products when I do elimination? No, only elimination products. Two things that are totally separated. They are really connected, very connected. But in terms of for our studying purposes, just consider substitution separate from elimination. They all both use the same substrate. What? Same substrate, I mean, even the same reactant, right? So, but they give you different reactions, right? Different reaction products. So that's why I would like to keep it separate. Okay? So in this case, we're only focusing on substitution products. This example above, which compound is substrate? Yeah, this is my substrate. Naming, don't worry about naming of the compound. In this case, it will be 2-chloropropane, or what we call it is isopropyl chloride. That would be the name. Why is it called isopropyl chloride? Because the chloride is in the middle, right? Which is the isopropyl. This is 1, 2, 3, isopropyl chloride. Okay. Once again, don't worry about the naming of the halides. I'm not going to ask for naming of halides, but just using them. Right? So you will guys will see always the compound written in a formula. Okay, so now substitution reaction, right? So the main reasons why the alkyl halides undergo. So the big question is like why, right? So why is are alkyl halides not happy? Why do they have to react, right? So are they not stable enough? No, they're not that stable. Why is that? It's due to the presence of that polar bond. So you see here in this compound, methyl X, well, in this case will be methyl, let's call it methyl iodide, okay? Iodide is more electronegative than carbon, therefore it creates a dipole. The dipole will put pressure on the carbon. Carbon is de-protected, de-shielded. So carbon will be delta plus, and of course the halogen is delta minus. That polarity, that polarization attracts the nucleophile. Remember, nucleophile is electron rich. Electron rich will attack electron poor always. So if there is any electron poor center, right, in my substrate, it will definitely be a target for a nucleophile. It's really nothing, it's not the stability and instability, it's just the polarity that exists in my substrate, what really brings that nucleophile, brings and attacks it. Okay, and it has to be on the alpha carbon. The next slide will show us what is an alpha carbon, but in the next slide, we will see what is an alpha or beta. But I just want to make sure that it's always that carbon, the one that holds the leaving group, is the one that is highly negative, or partially positive. Okay, the halogen will always act as a leaving group, meaning that that leaving group is always going to depart. Eventually, will depart. So that X has only a few minutes in the molecule. Doesn't really, it's not stable because the leaving group is stable by itself. So it wants to leave. It has a high electronegativity. We know that halogens are electronegative. Therefore, they want to be independent. They happen to be attached to a carbon, but they want to be separated from carbon. And carbon cannot let it go. Why? Because if carbon lets it go, then it will have an incomplete octet, which is even more unstable. So before that happens, the carbon, before letting go that halogen, which is the leaving group, it will wait for a nucleophile to occupy that space. Okay, and of course, that nucleophile that is coming in is not as electronegative, or maybe is not as selfish, right, as halogens do not share the electrons, because halogens, they have electrons, they're only selfish, they don't want, they are very electronegative, they don't want to share the electrons, right? So now, leaving groups, right? So what makes it a good leaving group? The leaving group is really associated with the acidity of a compound. That's why we studied acid and bases before this chapter 7. So as we can see here, the acidity increases, right, as you go from the bottom to the top, right? So ammonia is very basic, 38, pK of 38, and then iodidric acid is pK of -11, it's very acidic. So a good leaving group is really, the best leaving groups are the conjugate bases of strong acids. That means that they like to exist by themselves. Okay. So for example, why is HI so acidic? Because if HI dissociates, I minus is very stable by itself. That's why the equation is like this, right? It's mostly to the product side. I minus is stable alone, doesn't need to be attached to hydrogen. If it doesn't need to be attached to hydrogen, it doesn't need to be attached to a carbon. So it's a perfect and ideal leaving group. All these groups that you see here, they are good leaving groups. Iodide, bromide, chlorides. This group, we will see towards the end of this lecture. This group is called the tosylate group. Tosyllate. I cannot really write that well here. Tosylate, Tosyllate. Okay, and then water. Water is also a good leaving group. Now, what are the bad leaving groups? Fluorides, right? We talked about that before. OH minuses, alkoxides, terbutoxide, and amines or amide anions. They're really bad leaving groups. They are not. They're not. If you are having a compound that have those groups, definitely they are not going to be used as a leaving group. What about that one? Iodide, bromide, chlorides, perfect. Tosylates, OH, water as a leaving group, they work perfectly. Okay, so we will get familiar. Don't memorize it at the very beginning. You will see them that very often. That you guys don't really have to memorize the structure. By the way, tosylate, you don't have to know the structure of tosylate. Normally, tosylate, we just write it as TS. TS. Tosyl is TS, and tosylate is TSO. Right? So that's how you abbreviate it. You don't have to write the entire molecule like as you see here right now with a benzene ring, the sulfur, and the methyl. No, not at all. Here is the structure, right? So kind of like a abbreviation or location, like a GPS of an alkyl halide, right? So here we have an alpha carbon. The alpha carbon is the one that carries the leaving group or the halogen. The adjacent carbon is the beta carbon, and then the next one will be the gamma, alpha, delta, gamma, delta. After that is delta, epsilon. Yeah, that is the sequence. Alpha, beta, gamma, delta, epsilon will be the sequence for locations, right? So substitution occurs at the alpha carbon. Why? Why is that, right? Because remember that the halogen really applies the electronegativity. The polarity, right, is delta plus, delta minus. Is the beta position also feeling that delta plus? Yes, that feels it, but not as strong as the alpha. The alpha definitely suffers that effect of the electronegativity because it's right next to it, right? It's attached to it. So obviously, so the substitution will occur at the alpha carbon, not at the beta, not at the gamma. Why the alpha? Because it's right next to the halogen, which is electronegative. It's selfish. It's the bad guy of this movie, right? Now, the branching of the alpha carbon also affects the reaction mechanism for substitution and elimination. So we can distinguish the same way as we distinguished, remember, for the carbocations, primary carbocation, secondary carbocation, tertiary carbocation. Same thing applies to alkyl halides and also will apply to alcohols. This, for example, this alkyl halide is called a primary alkyl halide. Why is that? Because the carbon, right, the carbon that holds the halogen has only one branch, primary. Here is secondary. Why? Because the carbon that holds the halogen has two branches. And this one is a tertiary because the carbon that holds the halogen has three branches. Okay, so is there any quaternary alkyl halide? No, there is no way you can have a quaternary alkyl halide. Only primary, secondary, and tertiary alkyl halides. And the same thing is going to apply for alcohols. Primary alcohol, secondary alcohol, tertiary alcohol. Just imagine that instead of a Cl, you guys have an OH, right? The OH is the alcohol group. So that would be a primary alcohol, secondary alcohol, and then here we have a tertiary alcohol. We will be studying alcohols towards the end of this lecture. So just stay tuned and then remember this classification of the alcohols also towards the end of this recording, right? All right, so what happens in a reaction? So the reaction, I will explain it with models. I think that that's the best way how to explain this. Okay, so I have an alkyl halide like this. This one is my alkyl halide. Let me get it harder so you guys can see better. Okay, this one is my alkyl halide. You look at it and you want to name it, that would be ethyl bromide. The blue is a bromide. So this one is an ethyl bromide. So definitely there is a high polarization in this particular bond, right? So you see this compound. So there's a polarization between that carbon bromine that is polarized, highly polarized. So this carbon is not happy at all. Why? Because it has a delta plus, delta minus. So it wants that to leave. Then it will come somebody, which is a nucleophile. In this case, it's an OH. That's oxygen, hydrogen. So it will attack. So the attack between a nucleophile and a substrate can happen in two different ways. How are those two ways? First is the concerted reaction. What is a concerted reaction? It's one step. So this one is going to attack the substrate at the same time. Basically, let me show it like this. So this particular compound, yeah, it will be better like this. The OH comes in for this side at the same time this guy is leaving. So see, goes in, comes out. Okay, so that is one way. So as this one leaves the molecule, this one gets added to the molecule. That's one way. That reaction, we will call it SN2. That's an SN2 reaction. Okay. Once again, what happens in SN2? In SN2, I have my leaving group, but now there is a delta plus, delta minus. That is an electrophilic center right here because of the delta plus. My nucleophile will come from the other side. It's good that we are already learning the characteristics of this reaction. the nucleophile will attack from the opposite side, and this guy just leaves. And that would be my product. My product would be this. Now you say like, oh, Professor Navarro, why? Why is it attacking from the opposite side? Why are you just not doing this, right? Why are you just not doing, let's say like, okay, so attack from this side, just wait for this one to come on, right, come out, and then this one can be attached to it. Why can't we just do this? No, you can't do that. Why? Because remember that bromide, even though bromide is a good living group, but remember that it's very rich in electrons, has lone pairs of electrons. What about OH? Same thing. OH also has electrons. So you have electrons here and you have electrons here. Do you think that there will be some repulsion here? Of course, there will be some repulsion. So the OH cannot really be the same neighborhood as the bromide. It has to use the back door. Okay. So any similarity with the, any partnership is just a coincidence. But if there is this type of conflict, right? Basically this one cannot see this one, because basically the carbon is cheating on the bromine with the OH, so they cannot see each other. So what is the only way how you can do the reaction is by attacking from the other side. Okay, so as soon as this one, the carbon says bye bromide, then the OH comes in. Okay, so now the carbon is happy, right? Because it never lose anybody, right? It didn't lose the bromine. It just, as the bromine was leaving, the OH was coming in. It's a concerted process. That's what we call a concerted process, right? Now, what happens with the second one, the second reaction? The second reaction is called a stepwise, or is a two-step reaction. What happens in this two-step reaction? In this two-step reaction, what happens is that in this particular case, I will explain you why, but I need a more substituted substrate. Okay. So I have now this substrate. This one is also an alkyl halide. For the ones that are seeing it, I can identify it. This is called a terbutyl bromide. You can see the terbutyl. I'll just go around terbutyl, right? A carbon that has 3 methyls, like I always say that, like the chicken food, right? The chicken food, that is the terbutyl. Okay, so terbutyl chloride. So what happens in terbutyl chloride? So in this case, we have a two-step mechanism or a two-step reaction. Why is that? Because in this case, the OH can really attack the carbon simultaneously. Why? Because as you can see, this substrate is too blocked, right? The OH wants to come in from here. It can. Once it can't, I can't. Why? Because it's too hindered. It's too many groups. So what is the only option? So the carbon says, like, I want somebody else. I don't want this bromine here. I want bromine to leave. Then, but OH says, like, yes, I want to go in, but I can't, because is space, right? Space wise, right? I can't do it. All right. So what it's going to do in an SN1 reaction, which is the other reaction, SN1, is that the substrate will wait for the leaving group to leave. The substrate will become a carbocation. Where is the carbocation? Right here. The bromine is gone. Why did the bromine leave? Because the carbocation is stable. So here I have a carbocation. It will form the carbocation, and then the OH will have an easier way how to enter the molecule. Now you have this particular compound. Okay, 2 steps. Okay, so the first one is the concerted process. Like concerted process in the sense that I have my alkyl halide as the same time as the substrate. The substrate is losing the leaving group. The nucleophile is attacking. Right, it's a backside attack. Always remember, always like that. This one leaves, this one comes in. That is SN2 reaction, concerted, 1 step only. What about the SN1? In the SN1 reaction, you have 2 steps. It's a big molecule, then the leaving group leaves first. That's step 1. Step 1 is this, the dissociation of the leaving group. And then second is the nucleophilic attack. Once you have the nucleophilic attack, that's how you complete the substitution reaction, right? So it's a better way how to explain this reaction, definitely by using these models. All right, so let's continue with the lecture. All right, so we have a concerted process, right? The concerted reaction, and you guys can have the stepwise. So this one we called it SN2 reaction. I will tell you in a second why is it called SN2, and the other one, the stepwise, which is called SN1. Okay, so in the concerted mechanism, which is the SN2, it breaks the bond, right? And then at the same time, involves breaking of the bond of the leaving group and making the bond at the same time. It's a concerted process. What about the other one, the stepwise mechanism? No, you have the dissociation, loss of leaving group, which is a step that we learned, right, on chapter 6, loss of leaving group, then carbocation formation. That carbocation formation is going to be followed by a nucleophilic attack, the nucleophile attacks. Now that the carbocation is free, is single, now it can do the attack, right? So the outcome is the same. So leaving group out, nucleophile in. In the previous case, also leaving group out, nucleophile in. So it's the same outcome. It's only that it's different ways how to do it. So why are we learning all these details then if it's the same product? Well, there are some stereochemical details that are very important and they are different between the two reactions. Okay, so let's focus now on SN2 reaction. What do SN and 2 stand for in the SN2 name? So it stands for, I will tell you here, bimolecular. The 2 is bimolecular nucleophilic substitution. Okay, bimolecular nucleophilic substitution, but it's only too long, so that's why we call it SN2. Bimolecular nucleophilic substitution. What does that mean, bimolecular? Bimolecular means it's a kinetics term, meaning that the reaction, the kinetics of the reaction depends on 2 molecules. Okay, in this case, where is it? If you look at this reaction that you guys have right now in front of you, what is the reaction depending on? The reaction depends on the nucleophile and also depends on the substrate. That's why it's called bimolecular, because it's a concerted process. The 2 reactants are involved. What about in SN1? In SN1, it's called unimolecular. Uni because it's only one. Unimolecular nucleophilic substitution. Why is it uni? Because it's only one. Who? The substrate. We will see that into detail. I mean, with details when we do SN1. But I'm just telling you that here stands for SN2 bimolecular. Why? Because in the most difficult step of the reaction, the nucleophile and the substrate are involved. So the kinetics of the reaction depends on the concentration of the nucleophile and also the concentration of the substrate. How might you write a rate law for this reaction? Okay, so the rate law for this reaction would be K, concentration of nucleophile, concentration of substrate. That would be how I write the equation, right, for SN2 reaction, because it really depends on the concentration of the nucleophile and also the concentration of the base, of the substrate. Okay. So rate will be equal to K, which is the K constant, right? The K kinetical constant, nucleophile and substrate. How would you design a laboratory experiment to confirm this rate law? Okay, well, that is Chem 202, right? So we did a concentration. Oh, how would I design? I will just change the concentration of nucleophile, maybe half the concentration, and see how fast the reaction. If the reaction gets slower by changing the concentration of the nucleophile, that means that the nucleophile is important. And then I will change the concentration of the substrate. So if both of them are important and the time changes, yeah, definitely it's a bimolecular reaction. Okay, so we're not going to go into those details really about the kinetics. This is just a progression that came up here on this slide. Okay, now let's go into the stereochemical details. That's why chapter 5 was taught before this particular chapter. The stereochemistry. Remember stereochemistry that we had a chiral center. The chiral center can give you two-handedness, right? Let's call it handedness, but 2 types of enantiomer, R and S enantiomer. What happens in my reaction if I have a chiral center, right? Here you can see on this reaction that the S goes to the R enantiomer. What is this telling you? This is telling me that the SN2 reaction produces a full inversion of the stereochemistry. So if my starting material has an S configuration, that means my product is going to be 100%. And here there are no exceptions. That maybe that's one of the few things in organic chemistry that has no exceptions. That here you guys have full inversion of the configuration in the stereochemical configuration of the molecule, right? So why is that, right? So that's the big question. Why is that we have that it has a full inversion? So maybe I should just use my models, right? And then let's go back to our very first molecule that we had with the methyls. I have my bromide here. All right. So let's say here I will use another atoms, so you guys can identify them. Okay, so let's say I have some other groups. So I make it chiral. Okay, this one is a chiral carbon, right? Okay, so let's say that my priorities here are, let's put the bromine on the back. Oh, let's just test it like that. This my priorities here are, let's say bromine is 1, 1, 2, 3. Okay, so if I make it this 1, 2, 3, if I make this 1, 2, 3, that would be counterclockwise. But since the hydrogen is not on the back, I will call it, right? It's counterclockwise, should be S, but because that would be R, right? This particular compound. 1, 2, 3. S, but because hydrogen is not on the back, I switch it to R. Okay, what happens in that SN2 reaction? In an SN2 reaction, I have that the bromine, which is my leaving group, right? Remember, we're also using the green one as a leaving group. My bromine has to leave, but the nucleophile cannot really replace the bromine from the same side. It has to replace it from the opposite side. Okay? So remember that we have R configuration, right, for this particular compound. Okay, so this one is replaced by the OH, my nucleophile, from this side. So as this one comes in, this one breaks. So what happened when this one breaks? Now this guy has to be attached from this part of the molecule. Now it will be like this. I mean, you can understand, but it will be like this. It used to be the bromine here, but now it has to be the other side. So now let's do the assignment for the configuration. Now I have 1, right? I will do with another color. 1, 2, 3. What is the rotation? This is R, right? R. But because of the bromine that is in the front, right, it has to change to S. What happened? My starting material was R, and now it is S. It's a full inversion. Remember, there is no way how the nucleophile can attack from the same side. You can't do this attack. It has to be from the opposite side. That's the reason why the inversion is full. There is no way how you can have a different any chances to have retention. Okay, and that is demonstrated here in this the next diagram, right? So draw the transition state for the following reaction, which explains why SN2 reaction proceed with inversion of configuration. Yeah, of course. So here I have my compound, which in this case is chiral. The iris chiral. I have a methyl, and ethyl, and a hydrogen. So what happens with this carbon, right? That carbon has the methyl, has the hydrogen, and down is the ethyl. The transition state means that the SH will form a partial bond with the carbon, and at the same time, the carbon will be breaking its bond with bromine. Okay, so that is the transition state. The symbol transition state is that particular cross, double cross, right? So here you can see transition state, the molecule really is preserved, right? So the methyl, hydrogen, and ethyl, methyl, hydrogen, and ethyl, one is a wedge, the other one is a dash, right? And the ethyl comes down. So, but the bromine leaves from the opposite side, has to be from the opposite side. And that would be transition state. That explains why you have inversion configuration, because it's the opposite. Now, this transition state, and then I want to take advantage of this transition state for you guys to tell me how many bonds does the carbon have in this particular transition state? What is the impression that you get? How many groups are around the carbon? Count them. 5, right? It looks like 5. Is the carbon really forming 5 bonds? No, because it has half bond with sulfur and half bond with bromine. So they don't really count as a full bond. But space-wise, right? If we talk about space, it's really 5 groups around the carbon. What do you think of the transition state? It's really crowded, right? It's extremely crowded. And that's going to be very deciding for the reactivity trends of the SN2 reaction. So less sterically hindered electrophiles react more readily under SN2 condition. That's the same reason I was telling you a minute ago, is that SN2 reaction hates crowding. So all that people that hates New York City, definitely that is not for, I mean, that they are SN2 because it is too crowded. So methyl halides are going to be more reactive than primary because there is less hindrance here. Here, less hinder, and tertiary alkyl halides, they will never undergo SN2 reaction. Why? Because they are too hindered. And that's the example that I was giving you a minute ago, right? Remember, for this particular compound, this one. This compound is a tertiary alkyl halide. Tertiary alkyl halides, they will never undergo SN2. Why? Because the nucleophile is not strong enough? No, it's because it's too blocked. The OH wants to come in, is too hindered. There's no way how it can come to the nucleophile to attack really back. It is too, there are too many groups here. The transition state will look too crowded if I want to represent the transition state here. There's no way. What about secondary alkyl halides? Great. At least there is more room. What about primary alkyl halides? Primary alkyl halide, great, because there is more space. What about methyl alkyl halides? That's the most ideal because there is no hindrance, there is nothing. So that's why methyl halides react SN2 quickly. Primary, fast, right? Secondary, okay. Tertiary, no, too slow, right? So it's too slow, the reactivity with a tertiary alkyl halide that it can't even be measured, right? So the reactivity. To rationalize this trend, right? So examine the reaction coordinate diagram. Yeah. So that's what we will see in here right now. So that the speed, right? How fast a reaction moves really depends on the activation energy. If you look at the activation energy, that is going to start increasing as you increase the branching of the substrate. What feature of the diagram is relevant to rationalize the reaction rate? The reaction rate is important by the activation energy. That's how I can tell if a reaction is fast or slow. What feature is relevant to rationalize the thermodynamics? The thermodynamics, I have to rationalize the energy, right? Difference between the reactants minus, right, the energy of the products. That's for the thermodynamics. But for a reaction to occur, really, it's the energetics, thermodynamics, but how fast it goes also depends on the activation energy. And this is more or less a representation of how it tells you like how fast a reaction can be. So this one is with a methyl substrate. It has a small activation energy. Primary substrate, the hill increases. You notice the hill, it goes up, right? That hill. Secondary substrate is already high. It's a really relatively high activation energy. For tertiary, they don't show it, but I predict that it should be really high, something like that. It's too high that the reaction can really climb that hill, that penalty, right? Energetic penalty to do the reaction. It's too much energy that the reactivity is really considered like 0. That's why it says here, tertiary substrate react too slowly to measure. There's no way how you can measure it because the activation energy is really high. Okay, so what are the factors that contribute to the strength of a nucleophile, right? So now it depends on the nucleophile. Do I need a weak nucleophile, a strong nucleophile, right? So what is it? Like anybody can attack an alkyl halide? No, there are different types of nucleophile. The same way as you can have stable carbocations and stable carbocations, or let's say like primary alkyl halide, secondary alkyl halide, nucleophiles can also be labeled. So in this case, you can have a strong nucleophile and a weak nucleophile. For SN2 reaction, what you need is a strong nucleophile. Why do I need a strong nucleophile? Let's go to the models again. Okay, so a strong nucleophile is needed. Why is that? Because you remember that you guys have a delta plus, only a delta plus. So a nucleophile that is strong, that has a charge, that has a lot of electrons available, it has to be ready to attack the nucleophile. Why? Because this guy is only delta plus. Remember, it doesn't have a charge, it's only delta plus. So it has to attack, it has to be negative enough, has to be strong enough. This one has to be strong enough to invade, right? The the area of the carbon. What happens if you have a charge? Yeah, a charge is different because a charge definitely has an incomplete octet. So it needs an okay nucleophile or a weak nucleophile. So, but in our case, you are talking about a delta plus, right? So it has to be a strong nucleophile. Why? Because the receptor is not that positive. So this one, to make this happen, this one has to be very negative. This one has to be very negative. So it can access and can do the reaction. Okay. So that's why a strong nucleophile is needed for SN2 reactions. Now, the other million, right, 1 million question, like, how do I know what are the strong nucleophiles? How do I know what are the weak nucleophiles? Here is the list. Keep that list with you. Actually, memorize it. I mean, you don't really have to memorize it. In my previous classes or sections, what I always say, only remember who your weak nucleophiles are. Anybody else, you can consider it a strong nucleophiles. Okay, so water is a weak nucleophile. What is this ROH? ROH means alcohols, any alcohol, methanol, ethanol, propanol, anything that has an OH that has a carbon side chain. Okay? So, for example, let's go back. What is an alcohol, right? An alcohol, that R group can be, let's say, ethanol, methanol, isopropanol, terbutanol, anything. Really, this is what it means R. This is R. This is R. This is R. Okay. What about cyclohexanol? Yes, that's also R. Anything that has an alkyl chain, any carbon chain that is attached to it. Okay, that is an ROH, any alcohol. Or you say, oh, what about this compound? This compound is actually called phenol. Okay, PHENOL. Right? So phenol, they're also nucleophilic, but between the two, which one is more nucleophilic? The one that's more nucleophilic, I would say that is the alcohol, right? Because remember that this OH is involved in resonance. And we said earlier that electrons that are involved in resonance are not as nucleophilic, right? Because they are moving back and forth. This OH, no. This OH, the electrons are fixed. Electrons are fixed. So they can definitely attack at any moment. This one's no. Why? Because maybe the electrons are taking a stroll, right, on the ring. You never know. So that's why they're always involved in resonance. So these electrons are not as available as these electrons, right? All right, so let's continue with substitution. I like this chapter. You can definitely tell. Hey, so next one. So we have the weak nucleophiles. Remember the weak nucleophiles, right? This table right here. Anything else could be a strong nucleophile. And as you can see, the strong nucleophiles, you have I minus. Normally, they are all negatively charged. This table is missing one nucleophile that I use a lot. Those are the amines, RNH2. And also these, any type of amine. RNH2, RRNH, and tertiary amines as well, RRN. Okay, tertiary amines. I like to use those as the nucleophiles. Okay, alkoxides, thioxides. That is sulfite. Sorry, sulfite, alkyl sulfites, chlorides, bromides, iodides, hydroxide, cyanides, We are never going to do any experiment with cyanide. Alkoxide, right? Alkoxide means like it's the conjugate base of the alcohol, right? That's the alcohol, that's the alkoxide. We use it, and the alkoxide is used as a strong nucleophile. And the amines, right? I mentioned already. You should be able to determine if a nucleophile is strong or weak. But once again, I mean, you guys just remember that only the weak nucleophiles are water and alcohol, and anything else can be considered a strong nucleophile, right? In general, yes, anions are strong nucleophiles unless they're involved in resonance. If they're involved in resonance, their power decreases. Polarizable atoms are good nucleophiles. For example, iodide. Iodide is a better nucleophile than bromide, and bromide is a better nucleophile than chloride because of the size. Okay, the polarizability comes from size. Okay, so more polarizable atom means that it is bigger because it has more space to distribute the charges. So that's why iodide is better nucleophile than bromide, and then better nucleophile than chlorine. The solvent affects nucleophilicity. That comes later. So the solvent is very important before the nucleophilicity because of the stability of the transition state. Remember that the success of a chemical reaction really depends on how stable, how you can stabilize the transition state. That's why Hammond, right, was studying how does it look like, the transition state. Why? Because I want to stabilize it. Because if I can stabilize my transition state, I can make my reaction faster. Okay, so anything that you can do to stabilize your transition states, definitely that's going to help the reaction. Okay, so that's all the description for SN2 reaction. I'm going to now show in practice, right? So how do I do before we do E1 reaction? Sorry, SN1 reaction. I'll show you what is an SN2 reaction. Let's do some examples right here. Okay, finally, I'm doing arrows in this course. All right, so SN2 reactions. Steady focus. Please focus, locus. Right. Come on. Okay. So in an SN2 reaction, remember it's a concerted process. Okay. And it gives you full inversion, right? One step. What is it? A strong nucleophile. What else? Full inversion. Remember, the full inversion is only if the molecule is chiral. If it's not chiral, don't even bother. And then the trend is methyl, faster than primary, faster than secondary, and tertiary does not do any SN1 reaction, right? So that's what we mentioned, right, at the very beginning of this particular, right, the study of the SN2 reaction. Okay, so based on that, let's do these reactions. Let's say that I have this compound, bromide here. They put me with a nucleophile, let's say cyanide. What will be the product here? The product is that, what is the outcome, right? So the product would be, okay, so first I have to determine what type of reaction is this. Okay, so what I do is I go to my substrate, always start with the substrate. Don't look at the nucleophile yet. Go to the substrate, determine what is this. Okay, this one is a primary substrate, right? Primary substrate, clear, one branch. Okay, primary substrate falls under the category for an SN2 reaction. So it has to be SN2. Okay, now what should I do? Then substitute it. CN in, and bromide is out. Do I have to be worried about the stereochemistry here? Full inversion, full retention, full inversion, sorry. No, why? Because this carbon is not chiral. This carbon is chiral. Oh, what about it somewhere else here? There's something chiral. No, it's this carbon. My alpha carbon should be chiral for me to be worried about the stereochemistry. If not, don't even bother. So bromine out, CN in. That's all you guys have to do. Another one. Iodide. And I have sulfite. What is the reaction? I mean, the product. Okay, in the case of the products, I see that this one is my substrate. My substrate happens to be a secondary substrate. This one, secondary. Why secondary? Because it has two carbon branches. The other one is an iodine, right? Secondary. Can secondary do SN2 reaction? Yes, it can do SN2 reaction. Okay, so just substitute it, right? So in and out. Is this chiral? No, it's not chiral. Okay, just substitute it. SH in. What happened with the iodide? The iodide is on the side. Do I need to write this side product? No, not really. I mean, all what we care is the organic compound that you're producing. Let's do another one. Chloride now. And then I do a reaction with OH minus. Okay, what is the product here? Okay, what type of, is this a substrate? Yes, because it has a leaving group. The carbon that holds the leaving group or the alpha carbon, is it primary, secondary, tertiary, or methyl? Is secondary. Okay, secondary. Can it do SN2? Yes, it can do SN2. So let's substitute it. Oh, but before that, chiral or not chiral? Yes, it is chiral. Okay, so if it's chiral, that means that you guys have to produce, right, a compound that has the opposite configuration. So if the leaving group is in a wedge, that means that the nucleophile is going to be now on a dash. Okay, the OH comes in and the chlorine, of course, comes out. Chloride out. Chloride out, OH in. So now this one used to be a wedge. That means that the product is going to be a dash. Full inversion. Okay. Another example, another one with chiral centers. Let's say I have dicyclopentane. I have the methyl here and a bromine here. They tell me do it with another one that is strong, methoxide. Okay. What is the product for this reaction? Substitution product, right? Substitution product, because this one can also give you elimination product, but once again, we're only doing substitution. Okay, so do I have a substrate? Yes, the substrate because it has a leaving group. Do I have a nucleophile? Yes, this is a nucleophile. All right, so that means that it can undergo a substitution. What the substrate, what type of substrate do we have? We have a secondary substrate. Okay, secondary substrate can do SN2? Yes. That methoxide is a strong nucleophile, therefore it's going to be an SN2 reaction. Okay, so what should I do? Okay, substitute it, but first be worried about the chirality. Is it chiral? In this case, yes, it is chiral. It's not these 4 different groups. Then whatever you have, you guys have to invert it. Full inversion. This one will be my full inversion. You say, like, oh, but professor, why didn't you invert this method? This method should be full in, because it says full inversion. That means that everything gets inverted. No, full inversion means that it's only the carbon that is here. That is the one that's been attacked. This carbon was never attacked. Only this one was attacked. So if you are doing full inversion, do full inversion of that carbon. If this one is a dash, that means that the nucleophile now is going to be on a wedge. That's my product. Last bromide. Okay. These are the types of the question that you guys are going to get, right? Write the product, predict the product of a particular reaction. So you will be given the reactants and you guys have to write the products. Another type of reaction that you guys will see, another type of question, my bad. Another type of question that you will see is write the mechanism of the reaction. In that case, you guys have to show the arrows. Okay, so let's do one that we did. Okay, let's do the mechanism for the iodide. They tell me write the mechanism for this particular reaction. Okay, so anytime that you guys are going to write a mechanism, you have to write what type of reaction you are doing. Right now, we only study SN2. So of course, it has to be an SN2 reaction, but let's do the analysis. Okay, substrate, yes, it's a substrate because it has a leaving group. As a nucleophile, yes, it's a nucleophile because it's SH. Is it a strong nucleophile? Yes, a strong nucleophile. Secondary substrate, right? Secondary substrate right here. Secondary substrate with a strong nucleophile give you an SN2 reaction. Oh, professor, why are you specifying that? Because if you have a secondary substrate with a weak nucleophile, it would be SN1. But those details we will see in a minute, I mean in a second when we study SN1. So right now I'm just gonna go ahead with that. Secondary substrate with a strong nucleophile is SN2. Here, right? Secondary can be SN2. Methyl primary and secondary. Okay, let's continue. Now, arrows. The arrow has to show really the backside attack. So in this case, right, because I know that the SN2 is a backside attack. So my arrow should really show that. So the SH, I will do the arrows. The arrow attacks from the back, the opposite side as the of the iodide. And you're attacking with the sulfur, the electrons of the sulfur. I don't want to see electrons from the air. No. Electron from the charge? No. Electrons from the hydrogen? No. The electrons have to be displayed appropriately as they are coming from the electrons of the sulfur. The sulfur is the one that is doing the attack with its electrons, not the charge, not the air, not the arrow, not the hydrogen. So use the electrons and then do a backside attack. If the hydrogen is pointing to the left, do the arrow from the right. If the iodine is pointing to the top, do the attack from the bottom. If it's on the bottom, attack from the top, right? And then from the right, from the left, you guys know what I mean. The arrow should be clearly stated like this: backside attack, and the iodide leads from the opposite side. Okay. Oh my God. This one should show that the arrow really, that bond goes to the iodine. The iodine leaves with the electrons. This iodine has already 6 electrons, so now it has 8. But once again, you don't have to show really the iodine as a product, but here it's telling me the mechanism. So the SH comes in and then attack from the opposite side. Okay, good. Okay, another one that has the inversion, right? So we did another reaction with inversion, another mechanism. I think it was chlorine. They tell me write the mechanism for this reaction. I have this reaction. All right, so again, the same recipe. What type of reaction is this? This is a substrate because it has a leaving group. This one is a nucleophile. Okay, good. So it should be either SN1 or SN2. How do I know that? Okay, so let's see the substrate. Substrate is a secondary substrate. Okay, secondary substrate can be SN1 or SN2. It depends on what? Depends on the nucleophile. The nucleophile is a strong nucleophile, so therefore it's an SN2 reaction. If this one is a weak nucleophile, it will be SN1. But because it's a strong nucleophile, it's an SN2 reaction. Okay, next. Now that I know that I'm doing SN2, I know that it has to be a backside attack. How do I do that backside attack? The chlorine is pointing down. That means that my arrow should be from the top, like that. Clear? Any questions? No. Okay, good. So chlorine out has to be shown like this, opposite side. It would be wrong if I see this. You say, oh, professor, but this is opposite side. The arrow is on the opposite. No, you're attacking from the same side of the molecule. It has to be from the opposite side. Don't do this. Even if you do this, that will even be worse. So, right, that's bad and that's bad because you're attacking from the same side. You cannot attack from the same side. Okay, so you attack, leaves, and then that one, it will just immediately convert to this dash. So it's no big deal, right? So keep in mind that. Okay, so one mechanism that I would like to go over is the mechanism with the neutral nucleophile. We also said that the nucleophiles can be neutral. Let's see what happens with this particular compound. Let's say that I have, we said that tosylate, right, is also a good leaving group. That's a tosylate. Let's say that I attack it with methylamine. And my product is this amine. Write the mechanism for this reaction. Okay, write the mechanism. So the mechanism, I know that if we go through the same steps, I know that it's going to be an SN2 reaction. Well, it's the only reaction we're learning so far. So first arrow, what should I do with the arrow? Okay, nitrogen attacks the OTS. This one is an SN2 reaction, therefore it's a backside attack. The nitrogen with electrons attacks the back of the carbon. Electrons, not the methyl, not the bond, not the hydrogen, not the arrow, not the air. Okay, so electrons attack the back of the molecule and then OTS leaves. One step, remember, SN2 reaction is a concerted, one single step. You substitute it. Okay, what is the product? Well, it's inversion, right? Full inversion. Therefore, is dash NH2 CH3, right? The hydrogen never left. The nitrogen attacked, but the hydrogens are still attached to the nitrogen. That creates a charge on the nitrogen. Why? Because now the nitrogen has 4 bonds. 1, 2, 3, 4. Nitrogen with 4 bonds. Is this the product that they want me to produce? No, it has an extra hydrogen. So how can I get rid of that hydrogen? With a proton transfer. I need a base. I need a base to remove that hydrogen. Who can help me? Well, you have, what do you have in the media? Well, you have OTS minus, right? You have OTS because OTS minus left. So that one can help you. But you always have to choose the best base. Who is my best base? Either the OTS, which is the leaving group, but you can also use excess of the reactant, CH3 and H2. Out of the two, remember that this one is going to be an excess. So you have in the media, in the reaction mixture, you have more of this than this, right? That means that this one is the one that can do the proton transfer. So I need to target that hydrogen, and those electrons go back to the nitrogen. Okay. So the molecule would look like NHCH3, right? What happened with the methylamine? This guy is called methylamine. This methylamine stole that, so now it gets protonated. Oh, but this one was not listed in my products. That's okay. Here, as long as you produce the main organic compound, that's all we need. We don't need really the details. I mean, the small details. No, as long as you produce that one, which is the main compound, that's enough. That's what you need for your mechanism. Okay, I made it. Yes, so I'm done with the mechanism because I made what I was asked for. Okay, so don't worry about any of these small details, small molecules that they were really not present, but you can just produce them. And that is my main production. Okay, so that would be the mechanism. So you have to do this anytime that you guys are using a neutral nucleophile. Anytime you guys have a nucleophile, don't forget to deprotonate last. Don't just do the SN2. Yeah, just say like, oh, but I did the SN2. I should be done. No, you're not done. Why? Because your product is charged, and then you guys have to deprotonate it. That's why you have to use a base. And then for the base selection, you guys have to see what are the bases I can have. I can have excess reactant or OTS, which is my leaving group. You can use both, but really the one that is being used always, the convention is the excess reactant. Because remember, this one is more nucleophilic than this. That's why it is displacing it. The methylamine will never displace the OTS if this one is less nucleophilic than this. This one is more nucleophilic. That's why it can displace it. Okay? So in this the mechanism, it should be, so SN2 really ends here. This one is just a simple proton transfer. But in the mechanism, you have to show everything. Because remember, the mechanism is really all the steps that are associated with the transition from this reactant to this product. It might include proton transfer, CCRs, nucleophilic attack, anything. But you have to go from point A to point B. That's the main purpose for mechanism reactions, right? So those are the type of questions that you guys can definitely see on the on any quiz or any exam for this particular chapter. All right, so let's keep going. So now let's move on to SN1 reaction. SN1 reaction, as we went over already, is the unimolecular nucleophilic substitution. So here, there's also a comparison. There is also a variant, which is the SN1 and E1. Okay, so you can also do elimination as well as substitution. So you can see on this, in this particular reaction, that's the substitution product, and this one is your elimination product. We're only studying the substitution product, which is called SN1. The substrate is tertiary. Remember, in SN2 reaction, we said that this methyl, primary, secondary, tertiary does not exist, right? Does not react under SN2. In SN1, it's actually the opposite. In SN1 reaction, tertiary is the best, secondary is okay, primary is bad, and methyl never, ever, ever will do SN1 reaction. Okay, so the reagent is ethanol, right, which is not a strong base, but it's a weak base and also a weak nucleophile. So the E2, don't worry about that because we're not doing elimination yet. Okay, so in this case, this is a one-step reaction. So here is what you guys see. So you guys have your substrate, it's highly hindered. So the first step for it, an SN1 reaction will be the dissociation, or as they call it, ionization. Ionization, the cleavage, dissociation, ionization, anytime that you guys want to use. That step is spontaneous, and that is the most difficult step of the reaction. Why is this the most difficult step of the reaction? Why? Because you are going from a full octet, complete octet, to an incomplete octet, right? Incomplete octet. So if it's incomplete octet, definitely it's highly unstable. If it's highly unstable, that is the most difficult step. Okay, so the first step is the most difficult. How many molecules participated in that difficult step? Only one. Only your substrate participated. What does that mean? That means that the kinetics only depends on the substrate. Was that the same in SN2? No, in SN2, the most difficult step depends on the nucleophile and the substrate. They both are important. In SN1 reaction, no. The most difficult step only depends on the substrate. Okay, so after the carbocation is formed, the carbocation, you form the carbocation, right? It will either undergo substitution or elimination. In this case, SN1 or E1. Okay, so in this case, it's reacting with ethanol, but that's how they both, SN1 and E1, they start from the carbocation. So that's something that they share in common. This one is the mechanism for the SN1 reaction. Two steps, right? It's a stepwise mechanism. The first step of the reaction is the ionization or dissociation of the substrate. So I need a tertiary substrate. It dissociates spontaneously, loses a bromine, it's a loss of leaving group to form the carbocation. Then the carbocation, now that has more room, right? Because remember, it was highly hindered here. The nucleophile cannot really attack, it's too hindered. So it has to wait for the bromine to leave. When the bromine leaves, it's a carbocation. The carbocation has more space. Now that there is a space, now the nucleophile can attack. If the nucleophile attacks, then now it's in, it gets protonated, of course. That's the second step, is the deprotonation, and then here you guys have your substitution product. Okay, so the entire mechanism is actually 3 steps. This particular, yes, but really the SN1 reaction ends here. Here is the end of the substitution. It's only that you are adding a third step because you have to do an SN and SN1 reaction. Okay, but that's something common that we have seen, right, in another one, in the previous, right, the previous mechanism. Another way how this SN1 reaction is also named is solvolysis, as you can see here in the last sentence. Solvolysis, why is it called solvolysis? Because the solvent is actually the one that is being used as the nucleophile. If we go back, we have to go back really, I missed it, I think. Okay, so here, right? So if we look at this table, right? So my nucleophiles, the weak nucleophiles, they're all solvents. Water is a solvent, alcohols are normally solvents. So it definitely makes sense that the SN1 reaction is also called solvolysis, because all my weak nucleophiles, and that's something also I forgot to mention, is that SN1 reaction uses weak nucleophiles. SN2 uses a strong nucleophile. So for SN1 reaction, it makes sense that to be called solvolysis, because the solvent is not only acting as a solvent of the reactants, but also participates in the reaction as a nucleophile. Okay. This one is the coordinate, the reaction coordinate, the reaction energy diagram, right? So in that particular mechanism that we just saw, right, in this particular slide, right? So you guys have the 1 step, 2 steps, 3 steps. Now, which one would be the one that has the highest activation energy? I would say that this one, right? This first step has the highest activation energy. Why? Because you're producing a carbocation that has a high penalty, energetic penalty. What about this one, the second one? Is that going to be high or slow activation energy? No, actually going to have a lower activation energy. Why? Because I'm going from an incomplete octet to a complete octet. It still has a charge on an oxygen, which is bad, but everything is complete, has a complete octet, so which is great, right? And the third one should be even faster. Why? Because I'm going from a charged oxygen to a neutral oxygen. So let's see what we have. Exactly what we predicted. The first step has a really high energy cost. That's what happens right here. Right here, you have the high activation energy. The second one is not that high, and the last one is really fast, right? So it's a more stable step. So 3 steps. And what is the most difficult step? Of course, this one is the most difficult step. That's the one that has the highest activation energy. Okay? We already talked about the kinetics, that the reaction depends only on the substrate, the one that holds the living group, because that's the most difficult step, the dissociation and the formation of the carbocation. The carbocation, really, I mean, that is again the details, right? The carbocation is an intermediate. It actually exists. Where is the carbocation here? It is an intermediate. That's my intermediate carbocation. Here I have another intermediate, but really the intermediate for the SN1 reaction is the carbocation. So the carbocation, the more stable it is, the better it will be for the reaction. Okay. Now the loss of living group, right? So it is what forms the most difficult step, and then the nucleophile attacks. There are many details with the behind the SN1, and in this last sentence, what they are really emphasizing is that when you are using a neutral species as a nucleophile, remember that you definitely need to do a proton transfer at the very end, right? Which is my last step of the reaction. Okay, so let's see more details. I like to go do that by hand. Okay, so we're talking now about SN1 reaction. So we have the dissociation of the living group. And then I will use this. Where is my tertiary? My carbon. Okay, so this one is my alkyl bromide, right? Terbutyl. It's a tertiary alkyl halide. Once it leaves me with a tertiary carbocation, which is great. Tertiary carbocation is great. It's relatively stable. So that's why the reactivity trend goes from tertiary then to secondary. This is a secondary carbocation. The primary carbocation is definitely not existing, right? It's really slow chances that this one will be reactive. So the tertiary carbocation is the most reactive because it is stable. So basically, this carbon doesn't really feel the departure of the bromine. Why? Because it's already shielded by hyperconjugation, right? We discussed that on chapter 6. Hyperconjugation from all these alkyl groups really help the stability of this particular carbocation, right? So now, what happens with the carbocation or the stereochemistry? I want to use the models now for the stereochemistry. Remember in SN2 reaction that we said that the leaving group, right, had to be at the opposite side, right? The leaving group had to be as the nucleophile because they cannot see each other. So that's not an issue in SN1 reaction. Remember, SN1 reaction, the leaving group is gone. So now when the nucleophile comes, the nucleophile has two options. Remember that the carbocation, a carbocation has a p orbital and has the 4 groups, right? R, R, R. So it has two orbitals. So it can be attacked from the top or can be attacked from the bottom. So these two. So the nucleophile can do 2 attacks. It can attack from here or it can attack from here. 2 ways. What do you think are the chances to attack from the top or from the bottom? Theoretically, you would think that is 50-50. And that is really, I mean, that is true. It is the 50% chances to attack from this side and 50% chances to attack from the opposite side. 50-50, right? From each side. But actually what happens is that it's not like a real 50-50. They found out that they get a slightly more inversion than retention. So what is that in more inversion than retention? Means that they get 52%, more or less, 52% inversion and 48% retention. What is the inversion and retention, Professor? What is that? What is that term? Retention means that you get the same configuration, right? So if your starting material was R, your final product is also R. Inversion means that if your starting material was R, the product would be S in the opposite side. So in an SN1 reaction, since the carbocation is open, right? So you should have 50% from this and 50% from this. But in practice, they notice that no, they have 52% inversion, 48% retention. Why is that? That's what I'm going to explain you guys right now. So imagine at the beginning of the reaction, okay? So let's imagine that here I have my substrate. Let me put it in a better position. Yeah, I have my substrate. Let's put it like this, okay? So what happens at the beginning? What do you guys think happens at the beginning of the reaction? At the beginning of the reaction, you guys will have that the you will have that at the beginning of the reaction, the first step is the dissociation. The bromine is going to leave. But what do you think happens at the beginning? Do you think that the bromine is going to go like this, like Flash Gordon, like this? No. At the beginning, the bromine will slowly break off. Slowly. What happens at the very first seconds of the reactions? At the very first second of the reaction, this side of the molecule is going to be hindered. The nucleophile will come and then it wants to attack. Do you think that the nucleophile will have 50% chance to attack from both sides of the substrate? No. Why? Because the bromine is still hanging out here. The bromine is still in the neighborhood. So the nucleophile cannot attack from the retention side. At the beginning of the reaction, the nucleophile will only attack from the inversion side. What happens later on? Later on, the bromine moves away until it finally is out of the play. So now that it's free, now the nucleophile has the option to attack from the retention side and from the inversion side. So that explains, it's called the ion pair. That effect is called the ion pair. What is the ion pair? The ion pair means that even though the bromine breaks off, right, it's off the molecule, but this one is Br minus and this one is C plus. There is always an ionic interaction that holds them together. Always, always. There is some attraction because they are plus and minus. So that one will create, the bromine knows that has to go, but the electrostatics doesn't know. So the bromine leaves slowly because of the electrostatic attractions. And during that time is that the nucleophile cannot really reach this way. Has to wait for the bromine to go. Once the bromine goes, that's when it can attack from the retention side or from the inversion side. Okay, so that is the stereochemistry detail that can only be seen with the models. On paper, it's not the same thing. Okay? So let's continue with the slides. Another thing that we have to deal with, I mean, that thing about the ion pair that comes later, but I just wanted to use the here is the ion pair, the stereoselectivity, two products. In theory, you should get 50-50, right? So when an alpha carbon, right, as it says here, when an alpha carbon in SN1 is chiral, you obtain two substitution products, inversion and retention. Theoretically, should be 50-50. Recall that in an SN2 reaction is a backside attack. Therefore, only the inversion is produced. What happens in SN1 that you don't get 50-50? Leaving group will form an ion pair with the carbocation electrostatics, right? The Br minus blocks one side of the carbocation. Therefore, the nucleophile will only have one, which is the inversion side to attack. Once the bromine leaves, once this guy is gone, then that's when it can attack from that side as well. Okay, but that is the limitation. That's why inversion is slightly more than 50 and retention is slightly less than 50. Okay, so knowing that, right, since we have the details for the carbocation, I mean the SN1 reaction from the stereochemistry, now let's go to the rearrangement. Remember that your intermediate for this particular reaction, SN1, involves the carbocation production. As we also study on chapter 6, carbocations have a property. They always want to get stabilized. One way how they can get stabilized is by solvation. Yes, solvation is one way, but another way that they can do is rearrangement, which is CCR. We call it CCR, carbocation arrangement. So anytime, and then now listen, I mean, from today, okay, today on chapter 7 is the first time I tell you any reaction that produces a carbocation will potentially give you rearrangement. There is no reaction in which a carbocation does not rearrange. It will always want to rearrange if it can, of course, right? So if it cannot do rearrangement, of course, it won't do it. But the idea of a carbocation is always to gain more stability by rearrangement. So that's what you see here. So you have this product, sorry, this starting material, this substrate. You would be expecting this one, this product, right? Because bromide is out, water should be in. What happened? You actually see this particular product. Why did I see that product if that was not my study material? Remember, the only way how you can change the structure of a molecule is by doing a rearrangement. So this molecule definitely rearranged. They also noticed that in this particular case, another molecule, and then it rearranged. They observe a molecule that they were not expecting. This is what happened in this particular. Remember, primary carbocations are too unstable to form. So this kind of arrangement occurs as the living group leaves. Okay, so you guys have a primary substrate. I know that primary substrate, they don't really undergo SN1 reaction, but here they are making it do SN1 reaction. That's kind of like a contradiction for SN1, but let's see. Let's just keep going. Primary carbocation are too unstable to form. So in this case, the arrangement occurs as the living group leaves. Yes, because a primary carbocation cannot really exist. So here the bromine leaves, the methyl really migrates in kind of like an SN2 reaction. You can see that it has attack from the back, and they form a tertiary carbocation, and then now it's more stable. That's when the substitution occurs. Okay, so let me see. This is definitely better to explain by hand. CCR in SN1 reactions. CCR in SN1. So let's say that I have this compound, bromine. Okay, that's first reaction, right? So they tell me that let's do this reaction. Okay, so what should I expect here? Okay, so let's do the analysis again, right? Like we did in SN2 reaction. My analysis is that, okay, I have a substrate with a leaving group, and I have a nucleophile. Therefore, this one is a substitution, nucleophilic substitution. Next, is it SN1 or SN2? Okay, so first start with the substrate. Is it primary, methyl, secondary, or tertiary? In this case, it's a secondary substrate. Okay, secondary substrates can do SN2, and they can also do SN1. So which one should I do? SN2 or SN1? So in that case, it depends on the nucleophile. The nucleophile is the one that's going to tell you what it is. So what type of nucleophile do we have? In this case, I see that I have a weak nucleophile. Therefore, it's a weak nucleophile, it will go under SN1. What if it's a strong nucleophile? If it's a strong nucleophile, it will go under SN2. Okay, so that's what you guys. Should I do that with every substrate? No, you only do that with the secondary substrate. Okay, methyl substrates will always do SN2. Primary substrates will always do SN2. Secondary substrate, those are the tricky ones. They can do SN2 and SN1. Tertiary substrates, only SN1. Okay, that problem, this one is a problem, the secondary, because they can be either SN1 or SN2. Primary, always SN2. Methyl, always SN2. Tertiary, always SN1. There is no question about that. But the secondary, that's the issue. So what should I do here? So you will go to the nucleophile. If it's a strong nucleophile, do SN2. If it's a weak nucleophile, do SN1. Okay? So now that we know that detail, that small detail, small but very important detail, let's do this. Secondary substrate, yes, secondary substrate. What type of nucleophile? Weak, therefore it's SN1. What is the first step in SN1 reaction? The first step in SN1 reaction is the dissociation. SN1 has 2 steps, but the first one is dissociation. Okay, dissociated. And you get bromide, right? Br minus. Okay, I produce a carbocation. So theoretically, I should do, and then I should start and then do the attack. The nucleophile should attack. But does that happen? No. Before you do that, the carbocation itself, it will ask, can I do CCR? It will ask itself, can I do CCR? Let's see. Secondary carbocation. Let's write it with a pencil. Secondary carbocation. The neighbor is a primary carbon. The other neighbor is tertiary carbon. Can I do CCR? Yes, because I'm neighboring, I'm next to a tertiary, which is a higher order carbon. Therefore, I can do CCR. So let's do CCR. What am I migrating? Okay, so this carbon has methyls and also has hydrogen to donate. So let's migrate the hydrogen. The hydrogen will migrate. Remember, that's the correct arrow for migration. Migrates. The hydrogen will now be occupying this carbon, right? Will be here. And now this carbon will be the carbocation. Now I have a tertiary carbocation. Good. Used to have a secondary, now it's a tertiary, it's more stable. Now, can I do the attack, the nucleophilic attack? Yes, now you can do it. So the water attacks the carbocation. In this case, my carbocation is not prochiral, right? It has 2 methyls. Water still has the H. So I have to use somebody to steal that H. Who is going to be more water? Because the water, remember, is a solvent. So water will remove the H, and this one goes back to the oxygen. That will be my product. My product right there. That's my SN1 product. Another one, let's see. With a methyl chip, right? So let's do this one. Iodide, yes. With ethanol. Okay, good. So they asked me write the mechanism for this reaction and also predict the product. All right, so let's go through the routine. Substrate, yes, has a leaving group. Nucleophile, yes, can be SN2 or SN1. Let's see, substrate, secondary substrate, right? Secondary substrate means that it can be SN1 or SN2. I didn't gain anything. Now, how do I decide if it's SN1 or SN2? Depends on the nucleophile. In this case, my nucleophile is a weak nucleophile, therefore it's SN1. Okay, now that I know that I have SN1 reaction, I know that my first step has to be the dissociation. Let's do it in a separate molecule. First step is dissociation. Iodine leaves. Carbocation. As soon as you form a carbocation, the first step that you do after the carbocation is to ask if there is CCR. Always, as soon as you make it, that's the first question you have to ask. CCR, do I have CCR? Let's see. Secondary carbocation, right? This one. This one is a secondary carbon. This one is a quaternary carbon. Can I do CCR? Yes. Why? Because the secondary carbocation is next to a quaternary carbon. Definitely I can do migration. Can I do migration with the secondary? No. Secondary with secondary will never do migration unless the new secondary carbocation is stabilized at resonance, but that's not the case. Okay, so I can do I can do the migration here. So let's see. Let me erase this. So I'm going to migrate. This particular carbon has 2 methyls to donate, no hydrogen. So the priority says donate the methyl. Methyl migrates there, and the other methyl is there. So the one that gets the plus charge is this carbon, right? That's there. Good. Now that I rearrange, now I can do the nucleophilic attack with the ethanol. Ethanol attacks with the electrons, of course. Attacks. Oh, is this chiral? Yes, actually it is chiral. Right? Why? Because why is it chiral? Because it has a ring. It has a ring with a methyl. It has the methyl. So it is prochiral. Normally the carbocations are not called chiral. Because remember, to be chiral, you need to have 4 groups. So this carbocation doesn't have 4 groups, only has 3. So it cannot be called really chiral. Right? So what we call it is prochiral. Prochiral means that can potentially create a chiral center. In this case, this carbocation is prochiral. So in this case, I can do the attack from this side, or I can do the attack from this side, right? 2 sides, because it's prochiral. It's different, the attack. Professor, do I need to show it? No, you don't really need to show the arrow. Okay? In the mechanism, you don't really need to show the arrow, but the product you guys have to show it. You guys have to tell me what you are making. Okay, so let's say that the ethanol attacks. One of my products is going to be, well, my product will be OH. That's the methyl, right? OH got added. Oh, professor, you're not doing the stereochemistry yet. No, I'll do the stereochemistry last. The stereochemistry, I only want to see the products shown with the correct stereochemistry, not the mechanism, only the products. Okay, ethanol attacks is neutral, therefore it's going to be positively charged. I need somebody to remove that excess hydrogen. I will call another ethanol. The ethanol will remove the hydrogen and those electrons go back to the oxygen. So now here is where you guys are going to show me the stereochemistry. That's the product, right? I'm done. Plus that's what you guys should do. Okay, show both they are not enantiomers, both products with the R and with the S. Do I have to label RS? No, you don't have to label any RS. All you have to do is just draw both. Or you can do, or normally what you will see also, you either draw both, or what you guys can do, what normally the books will do, is you write one of them, and then you will put plus the stereoisomer. So you don't have to draw it twice. I know that this one is 2 plus the stereoisomer. Or this. Okay, the 2 products or this. That plus the stereoisomer. Oh, but what about this? Can I draw this? Can I do this? Let me see. This plus stereoisomer? Yes, doesn't matter. One of them and then write the word plus stereoisomer or draw both of them. Okay, so that is in the case that you are producing both products. All right, so let's continue with the theory. Okay, the solvents, right? So we're talking about the solvents, how they improve or they change the routes, not really the routes, but the speed of a particular reaction by stabilizing the intermediate and the states. In this case, for the experimental data on SN1 reaction, they noticed that the reactions actually are way faster in protic solvents. Protic solvents, I will tell you in a second what is a protic solvent. They improve the reactivity. For example, if the nucleophile is iodide, in methanol, which is a protic solvent, the reaction occurs at a speed of 43. Whereas in DMF, which is a polar aprotic solvent, is way faster. What about chlorides? Also, if you go from protic to aprotic, it goes from protic to aprotic, it goes faster. Why is that, right? Remember, this one is an SN2 reaction. What I can see is that in SN2 reaction prefers the polar aprotic solvents. Here's what you see. For SN2 reaction, polar aprotic solvent is best. So this one is the case for the polar protic, a polar aprotic. Yeah, sorry, this one I was just getting lost with this. SN2 reaction. Okay, so they raise the energy of the nucleophile, a polar solvent. So the activation energy is smaller. Okay, so the SN2 reaction gets faster in polar product solvent. Why? Because the level of the reactants is higher. So the activation energy in this case is smaller than in this case. So the barrier, right? The energetic barrier is smaller for in a polar product solvent. What happens in SN1 reaction? Actually, polar product solvent decreases it. It makes the lower activation energy, so the reaction goes faster. Remember, the solvent is not going to change it from SN1 to SN2. It will just accelerate or delay the reaction. It's not going to change nothing. In terms of the selection of the reaction. Okay, so now let's go over the solvents. What we call PPS and PAS. What are they, right? So they are a polar product solvent and polar aprotic solvent. What is a polar product solvent? A polar product solvent is a solvent, as it says, that is polar and it has hydrogens. Example of that, water. Water is the best example for polar, the PPS. Has a polarity, has delta plus, delta minus, right? Delta plus. So it's polar and it's product, meaning that the hydrogens are exposed, are part of the molecule. A polar aprotic solvent, which is PAS, polar aprotic solvent is actually not like this. A polar aprotic solvent is acetone, for example. If you look at acetone, where are the delta plus and delta minuses? The delta plus is inside of the molecule and the delta minus is in the outside. Do you see any difference between these two? I do see it. Another example of PAS is DMF, right? Dimethylformamide. Dimethylformamide. This is formamide. Yeah, this is DMF. Oh, dimethyl, my bad. Okay. If you look at this molecule, where is the delta plus? The delta plus is also inside. The delta minus is in the outside. Another one, DMSO, dimethyl sulfoxide. Where is the delta plus? Inside. The delta minus outside. So it is not that exposed. The delta pluses are not exposed. Delta plus are not exposed. What about here? They are well exposed. What about another one? Methanol. Delta plus, delta minus. The delta pluses are well exposed. What is the consequence of polar product solvents? Polar product solvents, they have the delta plus and the delta minus exposed, meaning that if you have a cation, the cation will be solvated by the delta minuses. Can they do this? Yes. Why? Because the delta minus are well exposed. They are on the outside of the molecule. So PPS can stabilize cations. What about PAS? Can PAS solvate cations? Yes, because the delta minus are exposed. Delta minus are out. That's great. So it can. So cations can be solvated by PPS and PAS. What about anions? Can anions be solvated by PPS? Yes. Why? Because the delta plus are exposed. See, the delta plus are exposed. Delta plus, delta plus, delta plus. PPS. What about PAS? Are the delta pluses exposed? No, the delta pluses are actually secluded. They are inside of the molecule, of the solvent molecule. Do you think that well, PPS, yes. Do you think that PAS can solvate anions? No, they don't solvate anions. What is the consequence of this in SN1 and SN2? Okay. Consequence in SN1 and SN2. Consequence of in SN2. Let's start with the SN2. Remember the reaction of the leaving group, bromine, you have OH, right? This OH had to attack from the opposite, right? What was the condition for this reaction to occur? Remember, what is the transition state? Transition state had, remember, it was very crowded, right? So if the anion is hydrated with water molecule, with solvent molecules, do you think that this OH can attack efficiently a crowded transition state? No. I actually need my nucleophile to be naked. I need the OH to be free of solvent. I don't want any solvation. I want it free. So if it's free, it can attack efficiently the substrate. Can I do that with PPS? No, because PPS solvates anions and cations. It will solvate my OH. I don't want that. That's why PPS is bad for SN2. What about PAS? PAS is great. Why? Because PAS will leave alone my anions. If the anions, let's say nucleophile, right, is free, it can do the attack more efficiently. That's why PAS is good for SN2. And PPS is bad for SN2. Why? If I put my nucleophile in PPS, it will immediately solvate it. So it won't be able to do the attack efficiently. Okay? That's for SN2. What about SN1? What is the most difficult step of SN1? The most difficult step in SN1 is the dissociation. That's the most difficult step. Why is it more difficult step? Because I'm creating an incomplete octet. But is there anything that I can do to stabilize this this particular intermediate? Yes. How can I stabilize ions? Cation and anion. How do I stabilize them? Solvating them. If I solvate them, they will be stabilized. So what of the two solvents is able to solvate cations and anions? The only one that can do that is PPS. PPS is able to solvate cations and anions, which is great for SN1. What if I do PAS? Well, PAS will only solvate cations. So this one will be well solvated, but it will not solvate anion. So the bromide will not be solvated. So you won't have stabilized the leaving group. And for this reaction to occur, you need both of them to be stabilized. Otherwise, the reaction will go backwards. So that's why PPS is good for SN1. PAS is not good for SN1. Why? Because it only stabilizes one of the ions, not the other one. You want to stabilize both. That's why you use PPS. In the case of SN2, it's a different case, right? In the case of SN2, I don't want my nucleophile to be hindered. How can I do that? Use a PAS, because PAS does not solvate anions, but PAS does solvate anions. So that's why it's so bad for me to use PPS in SN2 reaction. This is only to maximize or make the reaction faster. I mean, once again, it's not going to decide if a reaction follows SN2 or SN1. Okay, so let's continue. That was about the solvent effect. Substrate, the reaction. What is a better leaving group? A better leaving group is iodide. Iodide is a better leaving group than bromine, more better leaving group than chlorine, better leaving group than fluorine. We said already that fluorine does not really participate in substitution reaction because it's a very bad leaving group, right? We already explained why, because iodide is larger, right, in size, so it's more polarizable. If it's more polarizable, means that it can exist by itself. So that's why it's a better leaving group. Now, in the case of the stability, right, the carbocation, the stability of carbocation is really important. Tertiary is a good, is stable enough. Tertiary carbocation is stable enough to undergo, to be a carbocation. But now, Here there are some exceptions. Of course, we had exceptions. This one is a primary carbocation. This one is also a primary carbocation. But these guys are special primary carbocations. Why? Because they are stabilized by resonance. So anytime that you guys see a benzylic and you see an allylic carbocation, they can undergo also solvolysis, which is SN1 reaction. So these guys, even though they are primary, because remember that for SN1 reaction, we say that tertiary is more reactive than secondary, and primary does not really react, right? In SN2 was different. In SN2 was the opposite trend, but in SN1, this is the trend. Tertiary, secondary, and primary does not react. So primary does not react, but benzylic and allylic, they're primary. Yes, but they are a special primary. These are promoted, we can call them promoted primary carbocations. So they will still undergo. Why? Because they're stabilized by resonance. Those carbocations are stabilized by resonance. Therefore, they are not the conventional primary carbocations. They will be higher order, right? So they are resonance stabilized, therefore they will do undergo SN1 reaction. Be able to judge, right, whether or not a given alkyl can undergo an SN. Yeah, definitely you will definitely that later on we will determine, we'll study A1 reaction. So in some cases they can do SN1, in some cases they will do E1 reaction. But once again, we're not doing E1 reaction right now. We talked about the stereoselectivity already, right? So the inversion is favor. You have a slightly more inversion than retention. Okay, so let's now see how are we analyzing the this particular. Let's do now examples of SN1 reaction. The same way as we did for E1. So sorry, for SN1 reaction. Sorry, for SN2. Let's do reactions. Let's say that they give me this substrate, bromide. Come on, focus. And then I need a weak nucleophile, right? Let's say methanol. Predicted product. What would be the product here? Okay, tertiary substrate. Tertiary substrate definitely goes SN1 reaction. There's nothing really to do about that. Do I need to look at the nucleophile? No. If you have a tertiary, don't do anything. Just go directly to SN1. Okay. So is this chiral? No, this is not chiral. Then don't just a simple substitution. You have a neutral nucleophile. Remember, in neutral nucleophile, the hydrogen eventually will disappear. So if you guys want to write the product, always remember to remove the H and then just insert the nucleophile. That would be a very straightforward substitution reaction. Let's do this one. OTS. Yeah, this reaction. Okay? And then they say this one has water. Okay, good. Substrate, right? Analysis. Substrate, yes, has a living group, OTS, tosylate. Secondary substrate. Okay, secondary substrate. Secondary substrate can be SN1 or SN2. How do I decide? Only in secondary, then you look at the nucleophile. The nucleophile, I happen to have a weak nucleophile. If it's a weak nucleophile, that means that it follows SN1 reaction. Okay, SN1 reaction means 2 steps. Then I have to analyze if it's chiral. If it's chiral, no, not chiral. Then just substitute it. Since it's neutral, I have to remove one of the hydrogens, right? Only one hydrogen gets removed. Don't remove both. Only one gets removed. And then that's your product. Let's see one that has chiral centers. Yeah. Another one that we haven't used that much, chlorine. And they tell me mix it with ethanol. Okay. Substrate, yes. Secondary substrate. Secondary substrate with a weak nucleophile. That means that it's an SN1 reaction. Chiral, yes. Chiral, yes. So I produce 2 products. One with a wedge, one with a dash. ETOH neutral. Erase the H, OET, OET. Okay. You produce the 2 products. Or you can just write this plus stereoisomer. Any, whichever you prefer. OET, this is ethyl, like ethoxide, plus stereoisomer, or draw both products. Let's do one with CCR. Methanol again. Okay, secondary substrate, yes. Weak nucleophile, SN1. Chiral, yes, it's chiral. But first, you guys have to see if there is CCR. In this case, there is CCR. Why? Because my substrate is next to a quaternary carbon. So you guys have to CCR. The CCR, you just select which of the ones can get migrated. So it goes there, carbocation there, and then the methanol can go adds right to this particular carbocation. Or CH3. It's not chiral. My new product is actually is not chiral. So I don't really have to be concerned about the wedges and dashes. So this one has CCR. So the product that you should be displaying is this one. No, is it wrong if I don't do CCR and I just show this product? Yes, it is wrong. Wrong. You shouldn't. You always should be aware of the CCR. Okay. Now writing mechanisms. Okay, so let's write mechanism. Actually, let's write a mechanism with a CCR, so it's more comprehensive. Mechanism. So let's say that they have a cyclopentane, chlorine, okay? And they tell me mix it with water to produce 1-methyl cyclohexanol, cyclopentanol. Okay. First, identify the reaction. Secondary substrate, yes. Weak nucleophile, yes. SN1. Okay, now that I know that it's SN1, I know that I have to do 2 steps. The first step is the dissociation of the leaving group. Leaving group is out. After that, I have to ask if as soon as I produce a carbocation, I have to ask if I have CCR. In this case, I do. Secondary carbocation, secondary carbon, tertiary carbon. So I do a CCR. What am I migrating? The hydrogen. The hydrogen gets migrated. Okay. Now the carbocation goes to the tertiary. Then I do the chiral. Is it chiral? In this particular case, no, it's not chiral. So I'm only producing one product. Then I do the nucleophilic attack. My product is close, but not quite, right? So I still need that to remove that. So I'll bring another water molecule, and the other water molecule will attack the hydrogen and the OH. OH. That's my product. Okay. So that will be my end of the mechanism for this SN1 reaction. Good. Let's continue. We're almost done, I promise. Retrosynthetic of SN1 reaction. Remember that SN1 reaction, you have a carbocation intermediate. If it's prochiral, it will create both, right? Both stereoisomers. So that's why here it says draw them both, R and S. Or do the alternative, right? What I told you. Draw one of them and then write on the side plus the stereoisomer. Other substrates, right? So we got used to see only halogens, right? For alkyl halides as living groups. But you also have other alternatives that are used in organic chemistry. Out of those 3, mesylate, tosylate, and triflate. So really the most common that you guys will see in organic chemistry is tosylate. Tosylate is a big group, I mean it's a big molecule, but normally is abbreviated as TS, only TS, tosyl. Tosyl group is right here. This is the tosyl group. And once it's attached to the oxygen, that's why it's called tosylate, but it's used as OTS and when it's a living group. What is the OTS? OTS is really the reaction between tosyl chloride and alcohol. So if you have an alcohol, an OH group, and you OHs we know that are bad leaving groups. You want to make a bad leaving group into a good leaving group, you have two options. First option is to tosylate it. So you have an alcohol, use tosyl chloride in pyridine. Pyridine is a solvent that is used as a base. Tosyl chloride, pyridine is a very toxic, mostly for male. They have been reported some fertility problems for men that smell pyridine, and also it's a very unpleasant smell. So don't even try. I mean, with pyridine, it's very. It's not stinky. It's just a smell. I mean, it's difficult to describe it. That smell is I mean is horrible. I smelled it a couple of times in my life, but it's really not good. No good thing to smell. Okay, so going back to the class. So an alcohol is a bad leaving group. If I want this OH a good leaving group, then tosylate it. At tosyl chloride, you don't need to draw the whole molecule, just write TSCl. That TCl in pyridine will tosylate it. Now it's tosylates. That tosylates now is a good leaving group. Okay? Another option that you guys can do, alcohols can also be used as substitution if you protonate them. Okay, so if they get protonated, now they become OH2 plus. OH2 plus a good leaving group. So this one is an alcohol, a leaving group. And you treat them with a strong acid like HBr. Can be sulfuric acid, can be HCl. So as long as it's a strong acid, a strong and high concentration, so it will protonate it. The OH attacks or gets protonated by the HBr, you get OH2 plus. That OH2 plus now is a good leaving group. As a good leaving group can undergo SN2 or can also undergo SN1 reaction. Okay, so remember that alcohols can also maximize or become or be leaving groups because they are normally no good leaving groups. Like here's another example. So for an SN1 reaction, tertiary alcohol with HBr gets protonated. Now you get an OH2 plus. Now that is a good leaving group. Good leaving group leaves as by a loss of leaving group dissociation. Now it becomes a carbocation. The bromide attacks, and you get a tertiary bromide. Right? So that's another way how to prepare bromides. The strongly acidic conditions are protic conditions, okay, which could favor SN1 reaction. But since primary carbocation, it will go under SN2. Yeah, in the case that you have a primary carbocations, then it will go primary alcohols. They will undergo SN2. Secondary and tertiary will do more SN1 reaction. Okay, so the mechanism will be either SN1 or SN2. If it's a primary alcohol, it will do SN2. If it's a tertiary and secondary alcohol, will react via SN1. That's only about the stability of the carbocations that are produced. Here are strategies to synthesize. At this point, we should be able to synthesize nitriles. We should be able to synthesize ester, thiols, ethers, alcohols. So we are learning little by little. Just on chapter 7a, we can synthesize those 5 groups. Okay, so you have an alkyl halide, you mix it with cyanide, you get a nitrile. With an acetate, you get an ester. With a sulfide, you get a thiol. With an alkoxide, you make an ether. With a hydroxide, you make an alcohol. And then with a bromide, right, you can go back and forth between the bromide and the alcohol. Those are the ones that you can play with in terms of synthesis. You can synthesize them using the alkyl halide that we learned today. Okay. Retrosynthetic analysis, general steps. This particular case, you guys have to determine this one is called the Williamson ether synthesis. So here you guys have to determine which one is the best combination of starting material for this particular ether. So in this case, I can see, let me do it by paper, that's the best way. Okay. In this particular reaction, they tell me this. Oh, this is a molecule, and they told me that this particular molecule came from 2 reactants. One is going to be, of course, since the one is we need a substrate, and the other one, of course, is a nucleophile. Which one is which? So go backwards, right? Basically go backwards. So one of them, I see the oxygen. Definitely one side will have the oxygen. It can be like this. or it can be like this. Which one is better? This or this? Right? So in this particular case, any way I do it, so it should be an SN2 reaction because I'm using an alkoxide. Well, if I use this one, it should be an SN, right? Definitely an SN2 reaction. Let's see. Oh, what are my combinations? My combination is oxygen like that. That's my nucleophile. Or this my nucleophile. Okay, let's do it. CH3O minus, right? That is that. And my other option is this molecule with minus. If this one is my alkoxide, that means that this one is my alkyl halide. If this one was my alkoxide, that means that this one is my alkyl halide for the second case. Which of the two is a better combination? Remember, we're talking about an SN2 reaction, right? Secondary substrate. What about here? Primary substrate. In an SN2 reaction, what is better? Methyl substrate. What am I talking about? Methyl substrate. In an SN2 reaction, what is better? A methyl substrate or a secondary substrate? Methyl substrate. Therefore, this combination I should be using. Does that mean that this doesn't work? No, it works. It's only that this one is a better combination because I'm using an SN2 reaction. That one, there's nothing wrong. Well, why is this bad? Because the secondary substrate. Secondary substrate are more crowded. Therefore, they are not gonna work. Okay? That's what I mean, the disadvantage of this, right? Of this particular reaction can have different options. Now, something that I wanted to do is also intramolecular substitution. That's a very important topic that we need to discuss. So an intramolecular means that you guys have a leaving group and a nucleophile in the same molecule. There's nothing wrong with this. So you can see that this one has electrons and this one has the leaving group, right? So this one is the carbon that's going to get attacked. SN2 reaction. Why is it SN2 reaction? Because this one is a primary substrate. Okay, attacks my ring. Now I cyclize it. 1, 2, 3, 4, 5. Let's label them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The bromine used to be attached to 5, but now bromide is gone. So I have the plus there. That is called intramolecular reaction. What if I have this? Is it also intramolecular? Yes. Nucleophile and well, of course, I have to deprotonate this, right? If I deprotonate this, I just have this molecule. This one is called THF, tetrahydrofuran. Okay, this molecule, intramolecular, yes. But is it the SN1 or SN2? This one is an SN1. Why? Because it's a tertiary substrate. So really, the first step here would be the dissociation. And then attacks. In this case is 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5, 6. Carbon number 6 has 2 methyls. And that's how you get the product. Now, what should I do? Should I think more first? What should I do first? Intramolecular or intermolecular? Intramolecular gets priority over the intermolecular. This is intra, meaning that the same molecule has the nucleophile and the leaving group. Intermolecular would be what we just did here. Intermolecular, between two molecules. Always think intramolecular first. Can I have CCR even in intramolecular? Yes. What about the stereochemistry? Should I be concerned about the stereochemistry here too? Yes. Everything is the same. It's only that the only difference is that the nucleophile and the substrate are in the same molecule. That's the only difference. Imagine that there is nothing here. It would be two molecules. They can do SN1, but now they are tied together. So that this can still do SN1. Okay, so that is one of the restrictions, something I wanted to share with you, that in some cases you guys can have intramolecular reactions, right? Very important to consider and to remember. Okay, so now let's go back to the slides. Polar periodic solvent. So these are the example of the periodic solvent. I think that this one is the last slide for this chapter. The solvent effects for polar periodic solvent. These are the polar periodic methanol, right? You can see here methanol, ethanol. They all have the hydrogen well exposed here, 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 ammonia, acetic acid. See, the hydrogen is exposed. So you have guys have the delta minus and the delta plus. In this periodic solvent, no, you don't. Haven't seen that in years. Hexamethyl phosphoramide, acetonitrile, DMSO, right? So all those are polypropylene solvent. They are good for SN2, but they are bad for SN1. In the case of polypropylene solvent, they are good for SN1, but they are bad for SN2. It's the opposite. Polypropylene solvent engaging H bonding and stabilize anionic species such as good nucleophiles. They hinder, they block good nucleophiles. That's why they are so bad for SN2 reaction. Apolypropylene solvents stabilize. Apolypropylene solvents stabilize both cations and protic solvents. They made a mistake here. Protic solvents stabilize both cations and anions. That's bad. So aprotic only stabilize cations. How do these factors play into the strength of the nucleophile? Yeah, definitely, right? We already discussed that in the previous, right? The previous slide. So protic solvent and aprotic solvent. Definitely in the exam, you might see some questions about protic solvents and aprotic solvent, their properties, and also how they affect SN2 or how they affect SN1. Okay, so that's all I have for now. Please let me know if there are any questions that you like to see, or anything that you would like to share with me. Those are the slides. I modified these slides, and you noticed I modified the slides so I can only teach about substitution reactions. So this one is actually shorter than what is posted on the Blackboard, but definitely the content wise, I mean, it is the same material. Okay? So please let me know if there are any questions regarding substitution. Right now we only did substitution reactions, right? Only this part. And elimination reaction will come next. Okay? So let me know if there are more questions about this chapter.